location, the Central Pacific, the depths of the lagoon within the Kwajalein Missile Range. The date, September 1980. The event, the retrieval of a reentry vehicle, the conclusion of one of the most important tests in the U.S. Army's ballistic missile defense program. A Russian surveillance ship located near the Kwajalein Atoll monitored the mission closely, much as it had on previous tests. For the U.S. Army, it was a milestone, the final mission of the Systems Technology Underlay Test Program, and the most challenging because the target was of a special configuration involving a highly realistic threat. Most important, it was the final test in a series designed to validate systems technology for this type of terminal ballistic missile defense. A validation of nearly 10 years of development and testing, the legacy that is a major element of our ballistic missile defense program. ABMD systems technology came of age during the decade of the 1970s, a decade characterized by military and political instability, war in the Middle East, widespread international terrorism, the continued proliferation of nuclear weapons, the gradual erosion of détente, and most significant, the Soviets continued their deployment of improved intercontinental and submarine-launched ballistic missiles. This posed a major strategic concern to the United States, a situation that could bring the threat of greater political adventurism or even a preemptive ICBM strike. Against this background, the value and significance of the BMD systems technology program became increasingly clear. Projections made in the early 70s indicating that survivability in our Minuteman ICBM forces would be seriously jeopardized by the end of that decade proved all too accurate. Without a defense, such an attack could destroy much of the ICBM retaliatory capability of the United States. To meet this threat, a decision was made in 1972 to launch a major effort to advance significantly our Minuteman ballistic missile defense capabilities. Thus, the Site Defense prototype demonstration program was established in 1972 with the objective of developing a tactical system that could be deployed in the late 70s. However, in 1974, congressional redirection placed emphasis on advancing BMD systems technology instead of developing a prototype system for deployment. These new objectives have been pursued to the present. At the outset, a major subcontractor team was assembled to pursue the objectives and challenges of designing a BMD site defense system. The U.S. Army's Ballistic Missile Defense Systems Command was assigned the responsibility for technical management of the site defense program. The contractor team was guided by McDonnell Douglas Astronautics Company as systems contractor. Supported by General Electric Company that was responsible for the radar subsystem, TRW for the data processing software, Control Data Corporation for the computer, GTE Sylvania for the command, control, and communications subsystem, and Martin Marietta for the interceptor. Martin also developed the Sprint interceptor on the Safeguard program. The goal of this team was nothing less than solving the problem of defending U.S. Minuteman ICBMs against large-scale ballistic missile attacks. Such attacks would involve an ICBM complex in which the reentry vehicles containing the live warheads would, in a sense, be hidden in a dense environment of ICBM tank fragments, penetration aids, and decoys. This problem presented certain critical technical issues. To develop an automated, unmanned system that could start operation from a dormant state, to develop real-time engagement software capable of defending against even a large-scale ICBM attack, and be able to separate the attacking RVs and decoys from the ICBM tank fragments through a process called bulk filtering. Then, be able to identify the threatening targets by distinguishing between the real RVs and the decoys through a process called discrimination. In addition, the defense system envisioned would also have to operate in the severe nuclear environment that would result from our interceptor warhead detonations and successful intercept of the targets. Offensive bursts at undefended silos and blackout precursors. It was these critical technological issues that confronted the Army industry team as they initiated system design in 1972. The system they evolved was a unique combination of radar, software, and interceptor, controlled by powerful computers able to handle a full-scale ICBM attack. While radar and software design continued, a systems simulation center was completed in 1973 at the McDonnell Douglas Astronautics Company in Huntington Beach, California. It provided a central, fully equipped facility for simulating the system or major components in tests of system and subsystem capability against realistic attacks. It was also used as a test tool to aid in the design and testing of major system components. Tests were also made to enhance our confidence that the system could operate in a nuclear environment. The results of U.S. nuclear tests were used to develop analytical models that could predict specific blast, debris, and radiation loads. These models, as well as laboratory test data and non-nuclear experimental data, indicated that the critical components of the system could perform successfully under tactical nuclear environments. An important system objective was to achieve rapid deployability. This was accomplished by using a modular design concept for hardware units. For example, the radar computer complex and all the electronics are contained on 7 individual pallets. These modular units are assembled and tested at the factory. They are then capable of being operational in the field in a very short time. This short installation and test period was later demonstrated in under 9 weeks at the Kwajalein Missile Range. After 3 years of the Site Defense Program, radar fabrication was underway. Systems Simulation Center testing had started, and the following tactical prototype design tasks had been completed: system specifications, tactical implementation planning, life cycle costs, and advanced interceptor concept definition. However, developmental work on these tasks was discontinued in 1974, when Congress redirected the program from a prototype demonstration to a systems technology investigation and research effort. These program changes were in response to budget priorities and changes in U.S. strategic needs. Advanced interceptor development was stopped at the concept definition stage, but a technology base was maintained for high acceleration interceptors should subsequent development be required. Most effort was also stopped on the command, control, and communication subsystem because currently available technology could support rapid development of an appropriate network. Emphasis was now placed on advancing the technology of the key subsystems: radar, data processing, and software. At the Systems Simulation Center in California, the development of mission test software and subsystem integration continued. To perform these functions, the center was equipped with computers of great capacity, such as the CDC 7700, a commercial off-the-shelf system that was modified easily and economically and used later for the test program at the Kwajalein Missile Range. The center performed such functions as development and test of real-time engagement software, subsystem integration, and system and subsystem simulated testing that generated engagement and intercept data using simulated threat models depicting ICBM and SLBM attack scenarios. Out of this effort evolved engagement and test support software programs containing instructions for controlling an entire test mission. A software system capable of acquiring and identifying the threatening objects in full-scale ballistic missile attacks. It provides for computer-controlled, unmanned operation after initial manual activation through the command and control system. It controls specific functions, such as system activation and the capability of operating from a state of dormancy. Initiates radar control, bulk filter, and performs precision tracking and RB discrimination. Validation of these BMD systems technology designs was accomplished at the Kwajalein Missile Range using live targets launched from Vandenberg Air Force Base in California. The Kwajalein Atoll, located in the Marshall Islands, is a coral reef formation enclosing a large lagoon that is ideal for radar missed-distance scoring and reentry vehicle recovery. Consisting of nearly 100 islands, one of which is MEC, it is the test site for the systems technology program. Here, construction of a systems technology test facility was started on MEC in November 1974. The structure would house all the radar, data processing, and support equipment, as well as a mission control room for monitoring the test program. While work progressed at MEC, everyday living continued on nearby Kwajalein Island. This Army-administered community is home for military personnel, as well as civilian engineers, technicians, and support people. They live in small houses, trailers, and bachelor quarters. Shop in a supermarket and department store. Go to school. And enjoy leisure activities. But this is not a typical suburban community. Here, you live with the people you work with, a close-knit community like the small towns that were once so prevalent in America. An essential part of this community are the Marshallese people themselves. Over the years, the U.S. Army has sought good relations with the Marshallese and has supported them in their evolution from trust territory status to independent nation. By 1976, the Army Corps of Engineers had completed construction of the test facility, and system components began arriving by air and sea. These were shipped on modular pallets, ready for quick installation and checkout in the test facility. 9 weeks after arrival of the equipment, the test facility was operational and ready to support system testing. 9 weeks, a convincing demonstration of rapid installation, and all completed by the scheduled milestone date. Since major system components were integrated for the first time, extensive testing was performed to characterize the system prior to the first live mission. However, by May 1977, final preparations were being made at MEC Island for the first mission test of the new system against live targets. All missions were launched from Vandenberg Air Force Base using Minuteman intercontinental ballistic missiles. Since Air Force ballistic missile programs were engaged in testing a variety of reentry vehicle configurations, these launches provided targets against which systems technology components were primarily tested. After only 30 minutes of ballistic flight, the reentry vehicle, simulating a warhead and booster tankage, approached the Kwajalein missile range. Atmospheric reentry initiates a slowdown and causes breakup of the ICBM booster tankage. The result is an incoming threat complex consisting of tank fragments, penetration aids, decoys, and reentry vehicles. In order to ensure a high probability of detecting the RVs, it is necessary to reduce first the number of objects in the cluster to avoid overloading the system's radar and data processing capabilities. This is the function of bulk filtering, which was tested from altitudes exceeding 110,000 feet down to below 80,000 feet, and is accomplished by radar Doppler techniques that measure the velocities of all incoming objects. Because tank fragments move at slightly slower speeds than the RVs and closely matched decoys, they are eliminated from consideration by the radar, leaving the decoys and warhead clearly identified and placed in precision tracking. The next defense stage is discrimination, a function that distinguishes the RVs from the decoys. This was tested from altitudes exceeding 100,000 feet down to below 50,000 feet. Discrimination is accomplished by sophisticated data processing techniques that detect differences between the body or wake characteristics of the decoys and the RVs. Once identified, the decoys are eliminated from consideration by the system, leaving only the RVs to be engaged. The final stage in a tactical site defense deployment configuration is the intercept and destruction of the threatening RVs by means of advanced sprint-type interceptor missiles. The reentry phenomenon is difficult to capture on mission tracking film, but this is the live action equivalent. Pinpoints of light scattered across the sky and descending over the Kwajalein missile range. The first mission in 1977 was a target of opportunity. That is, it was not specifically dedicated to the systems technology program, and it resulted in successful data gathering on the reentry vehicle. Missions involving targets of opportunity continued over the next 4 years and included such tasks as verifying bulk filtering techniques against a live target and demonstrating a capability to operate from dormancy. The system was shut down for 17 hours prior to the arrival of the RV. After the target was launched, the system was automatically activated and proceeded to successfully track the RV. In January 1979, the first dedicated systems technology program mission was conducted. This was the first attempt at detection and tracking of an RV within the clutter of tank breakup fragments. Signal returns from the tank fragments were automatically analyzed by the radar in order to eliminate them successfully by bulk filtering and allow subsequent tracking of the reentry vehicle. The RV and decoys moved ahead of the slower tank fragments. As the threat complex approached Kwajalein, positive identification of the RV was achieved in the discrimination phase. All accomplished by automatic operation of the system's technology radar and computer on Mech Island. Here is another look at the same reentry from a head-on view. This first dedicated mission was significant in that the RV was detected at the first opportunity in the presence of tank fragment clutter and was tracked accurately until it passed the limits of the single face of the phased array radar on Mech Island. The second dedicated mission presented a further challenge to the system. It was designed to put the reentry vehicle and 2 decoys in the tank breakup clutter. A 3rd decoy was positioned to re-enter outside the clutter for comparison purposes. The system successfully tracked the re-entry vehicle and 3 decoys and successfully discriminated the re-entry vehicle. A 3rd dedicated mission involved the tracking and discrimination of a re-entry vehicle with a modified heat shield. The heat shield had been modified to present a more realistic image to the radar, more like an actual Soviet threat. Again, the system successfully detected, tracked, and discriminated the RV. Then, in September 1980, preparations were made for the final dedicated mission, the most sophisticated test in terms of the target to be made on the system. As mentioned earlier, the target was specially designed to provide a realistic test of the discrimination function. Additional personnel arrived on Kwajalein to participate in this final effort. The recovery ship Neptune was moved into position for retrieval of the RV from Kwajalein Lagoon. An ARIS radar ship was added to the land tracking capability to validate the database available for future BMD system designs. This is the Kwajalein Missile Range layout of the final mission, showing the position of the ARIS radar ship, the Neptune recovery ship, the re-entry corridor, and the recovery area. An optical sensor was also launched as part of a BMD experiment against RVs outside the atmosphere. At the Range Operations Control Center on Kwajalein Island, U.S. Army personnel coordinated mission countdowns, monitored safety considerations, and maintained communication links among the participants in this milestone mission. At Vandenberg, some 4,000 miles away, the Minuteman soared from its silo. Following bulk filtering, tracking, and discrimination, the RV is identified. The mission ends with splashdown in the Kwajalein Lagoon. As we saw in the beginning of this history, the re-entry vehicle is recovered from the Kwajalein Lagoon. All objectives of this final mission were fully achieved, demonstrating the ability of the system to perform successfully against a highly sophisticated and realistic target. This event signaled the completion of a 4-year BMD test program, in which the key technological goals of detection, bulk filtering, tracking, and discrimination had all been achieved. In all, the system's technology underlay system was tested in 50 missions over the Kwajalein Missile Range, with a near-perfect success rate. A legacy of experience, learning, and technical database applicable to future BMD development.
The successful live underlay test program at Kwajalein climaxed nearly a decade of gratifying progress in advancing our ballistic missile defense technology. The data processing system in this BMD simulation center was used to support the development and the field testing you have just seen. During the site defense and systems technology programs, we faced several critical technical issues: real-time engagement software development, operation from dormancy, operation in a nuclear environment, bulk filtering, and discrimination. We have essentially resolved these complex technical issues, which are the operational core of the system. Therefore, the technology exists today to build a BMD system that can detect, discriminate, and intercept warheads even in the extreme environment of a massive ICBM attack. The system, based on this program and earlier BMD development, works. The ability to discriminate, to distinguish a live warhead from decoys, was one of the more difficult technical tasks solved. And our real-time discrimination performance during Kwajalein testing shows that we can positively identify incoming RVs with a high degree of success. All this means that today we have the combination of experience, hardware, software, and a nucleus of personnel that can be expanded to provide important defense options now and in the future. In the near term, this technology legacy would allow us to complete development and deploy a site defense system to protect existing Minuteman forces against Soviet first strike capability. The BMD technology gains and testing experience of the 1970s have also laid the groundwork for future defense systems. For example, we are applying this technology and experience to a pre-prototype demonstration program which will develop and test a new concept for low-altitude defense for the MX intercontinental ballistic missile system. Low-altitude defense system development work will benefit directly from the engagement software experience and discrimination database, the concept of operation from dormancy tested at Kwajalein, the site defense radar designs, and the design concepts and technology for a new high-performance interceptor. The low-altitude defense program will also open the way to creation of options for the defense of existing Minuteman sites and other hardened strategic assets. In addition, low-altitude defense can function as the underlay of a layered defense system, the most cost-effective and robust BMD defense concept for the protection of U.S. strategic elements. This highly successful systems technology program has provided us with a new set of BMD options and has reduced significantly the lead time for deployment of a ballistic missile defense system. As a result, the site defense program has provided a legacy that lends promise to help preserve our nation during the critical years that lie ahead.